Thanks. First of all, thanks a lot for having me on the agenda. And would have been great for me to join. It's really unfortunate that I'm not able to be there with you physically. Personally, I have a strong bond with the United States since actually yesterday was on the day exactly 25 years ago since my daughter was born in Raleigh, North Carolina. So I think as a family, we're always connected to the US. Uh, I think you already mentioned my background, but a few words. I got a master's in electrical engineering from the Royal Institute of Technology in Stockholm back in 1992. I've been in the energy industry since then and 26 years with ABB. We started the company MindStorage in 2020, and I've been this co-founder and CEO since then. And I think our partner, Michigan Tech, has been represented by Tim earlier. So I'll skip that part, but also mention a little bit about not only us as MindStorage, but also our partner, Darlin Power. And that will be part of the introduction. And since the topic is about how energy storage and MindStorage as one of the solutions for energy storage large scale can support the system, the electrical energy system, I'll present some results from a study that we did a couple of years back, and then also show a couple of real cases in Sweden and also where we stand together with Darlin and MTU in the US. But starting off with the introduction, Darlin Power, as you may know of, is a cooperative based in the upper Midwest and in 4 different states. And they have both generation and transmission, and it's a cooperative, as I mentioned, not for profit. Quite significant with Swedish measures, but in the US, of course, everything is bigger, so they may not be known by everybody. Headquartered in La Crosse, Wisconsin, and close to 4,000 miles of transmission lines. But even more interesting is what they have on the renewable side. And if we look at the left-hand corner, they have something that is being supported by the new ERA, Empowering Rural America program, which is going to be wind of almost 600 megawatts and solar of more than 400 megawatts installed during the next number of years. Their system today is also staffed or filled with coal, natural gas, and oil-fired power plants. So this is the fossil-based part of their grid. And these are the sources that we typically in an electrical system look upon as reliable, dispatchable, and the base load that keeps our electrical grid stable. What is interesting is the way the grid, the mix of the production resources is about to change here in the next number of years. And as you can see, there's going to be a lot more of wind and solar, which has a completely different behavior from an electrical perspective, given that it's not dispatchable. You simply have to rely on when wind is blowing and sun is shining, as we all know. And this will be a complete change in the electrical system. And why this is important, that's why I have the study that I will present a little bit later. But given this outlook and this future scenario, Darlin contacted us about 3 years ago, actually, on the day. And who are MindStorage? As a company, we're, as I mentioned, a startup starting in 2020, completely based on risk capital. So we have a cap table of about 50 different shareholders, primarily business angels and family offices, but also 2 institutional investors. One of them is out of EU originally, a VC that's now having about 150, 180 different type of startup tech companies in the energy industry. And our business idea is to take ideas such as in this context from qualification phase, develop the product, build them, manage the whole construction phase, and also put them into operation and stay on as part owners of the sites. And some people are not familiar with the product development company. So typically I describe it with lower section of this slide, where the business case is really the center of it, and that's where we are focusing, and then we're going all around this circle. Everything from having a good relationship with the local community and going clockwise here, securing agreements with landowners to make sure that we can actually establish these kinds of projects later on, looking at the environmental aspects and the permitting aspects. To build a facility for energy storage, of course, we need a good connection. Also, to be able to justify the business case, we need to do conceptual designs, engage contractors to understand the total capex. We also need to engage with equipment suppliers, and so far we've been strategically 100% together with Voith Hydro, who is a global player in this market when it comes to pumped hydro and hydropower equipment. But last but not the least, also we need to know and understand the market and if there are potential off-takers for the services for this kind of services that an energy storage provide. So that's us as a company. What is the mine storage concept? One of the values when we speak to investors is that we use proven technology, but we set it up in a new way, in a new context. And starting from the well-known technology, which is called pumped hydro. Basically, what that is, for people who's not familiar, is that hydropower plants, when you have water flowing from a higher elevation to a lower elevation, and at the lower elevation you have turbines rotating, connecting to generators, creating electricity simply. And then to create a pumped hydro facility out of this, you need to also add equipment to work in the reverse. So basically being able to, through a motor, drive a pump and then pump the water the opposite direction. And once we have pumped the water to a higher elevation, that water itself, simply by gravity and the height difference, has then gained more energy. So that is the principle with pumped hydro, to work with water and gravity. And what we do is basically just putting these systems below ground and utilizing height difference below ground rather than going in mountainous areas. And there's a number of values and benefits with this. One of them is that there's not mountains all around the world. There's a lot of countries with flat areas only. And when we look at location of mines, there is a database of closed mines, mindat.org, which has more than 1 million abandoned or closed mines around the world. So there is a lot better distribution of mines than there is of mountains in the world. So this is a concept that actually opens up for pump storage as an energy solution compared to if we only use a traditional solution above ground. It's also valuable to see that at closed mines you have infrastructure that can be reduced, which in turn can reduce the total capex and also reduces the environmental impact. And in that context, also the regional or the local aspects in terms of creating changes for the local communities. We also look at the machine configuration. My thinking was not to go into that in detail, but we have slightly different setups of the machines so that we can also add technical capabilities and additional system value from an electrical perspective. But if someone is curious about that, I'll get into that in the Q&A. So that is the principal concept. And before getting into the system study and also our products, I just wanted to mention what was presented by McKinsey not too long ago, when they look at the global need for energy storage by 2040. So their estimate is that there's a need for 140 terawatt hours of energy storage around the world. And that's quite a difficult number to comprehend. But if you compare that to Tesla cars, that would be 1.5 billion Tesla cars. And that amount of energy is the same amount of energy that Sweden would consume as a country over a full year. And where are we today? We're at 10 terawatt hours today. So there is another 13 times or 14 times that we need to add the next 15 years. And more than 90% of those 10 terawatt hours are out of pumped storage facilities around the world. And less than about 4%, 0.4 terawatt hours is based on batteries. So even though there is a boom of battery installations around the world today, it's still a very small portion of the total storage capability, and also a very small part of what's needed if we can trust the analysis and the studies done by McKinsey, which I think we should. So that's a little bit of the introduction and the background and where we come from as a company. When I talked to the board a couple of years ago, we talked a lot about what is the market need for mine storage. And in that context, we initiated a study with the University of Uppsala and also a branch organization in Sweden. And the result of that one I'll come to. But before that, I think just to put Sweden as a context for you in the US, I have this slide where we compare Sweden to California in a few aspects, primarily from an electrical system point of view. But we're about a quarter of the population, about the same length in terms of transmission lines, or sorry, the length of the state of California versus Sweden. Transmission lines is only about a third or a little bit more than a third. Production capabilities almost the same, but the installed power in California is about twice the size of the installed power production capabilities in Sweden. So we're to some extent not too far away from California, but I must say I envy the sunshine in California and the coast there. So that's we're far away from that, unfortunately. Um, Sweden is also a very small country, as you understand, from a GDP point of view, but as such still have the tradition of some very classic companies in the traditional industries like metals and mining, pulp and paper, forest, and also into machinery and automotive. So some of these brand names I'm sure you recognize. We also have about 80% of the European iron ore deposits, and that's where LKAB comes in, which is the state-owned mining company. We also are the fourth largest exporter of forest industry products in the world. And according to at least our companies here, Volvo and Scania, they are the number one and two in the world in terms of supplying heavy trucks. So there is a number of companies that are in the forefront globally. From an electrical point of view, we have been fortunate that we've had a mix that is really cost competitive and also very reliable, which has been one of the key success factors for the industry in Sweden. And this goes back to the 70s, and you can see before the 70s, basically all the power production was based on hydropower. And then from the middle of the 70s into the middle of the 80s, we had our era of construction of nuclear power plants. And then since the middle of the 80s up until now, basically, you can say that half of the production has been hydro and the other half has been nuclear power. So really a system where the base load and dispatchable load from a kind of longer perspective in nuclear, and also the hydropower resources where you have an excellent controllability to make sure that your system is not long-term stable only, but also in a short perspective in terms of frequency regulation. So it was an ideal system, and as you can see, even though Sweden grew as a company from a GDP point of view, also efficiency measures continuously allowed us to stay at the same production level, as I said, about 140, 150 terawatt hour per year for 40 years, basically. Um, but things change, and we all know that we are now looking at how can we phase out fossil fuels. And as I said, Sweden is a small country, but several of the companies here are global, international, and are aiming to stay in the forefront. And if we look at the industry and the impact on the climate, many of these companies have observed their impact on the climate in terms of emissions, and also want to be in the forefront going forward. So some of these companies are really, LKAB I mentioned is a mining company, and Hybrit and Stegra are two companies now aiming to produce fossil-free green steel. SMA Mineral is a cement company, also with a high portion of CO2 emissions in their production. And Volvo Trucks is a company who's aiming to reduce their CO2 footprint to the maximum possible. In addition to those classic industry companies, we're also having some companies that are global and well known by you, like Microsoft, Facebook, and Amazon, who are located in some of their data centers in Sweden and in the Nordics for some of the reasons, but one has been that there is renewables and fossil-free electricity production that they see as a value in their way to also aim for a fossil-free and a completely CO2-free footprint. But we're also having a couple of companies who are in the energy area, which are aiming to introduce production of hydrogen for future solutions into industry and transportation, which are really high consumers of electricity. So all of that put together has been observed and done by several entities, both on the governmental level, but also on the industrial level in terms of different 2045 scenarios. And typically they end up in somewhere in between 300 and 500 terawatt hours in consumption per year. And that is actually a 2 to 3x versus where we've been at for 40 to 45 years. So this is a huge change for the energy industry and the electrical energy industry in Sweden, and quite a challenge for the whole society. And one of the aspects that we wanted to look at, that was to compare in this study that I mentioned, that was to look at a couple of different scenarios how to solve this. If the industry and the society will need us to add production capabilities of 2 to 3 times of today, how will that be solved? And the TSO, the Swedish Transmission System Operator, developed a couple of scenarios that we then investigated. And this is a summary of 2 of them. And in these 2 scenarios, we're starting off with the 40 gigawatt of installed capacity for production and about 150 terawatt hours of energy consumption and production. And in the one scenario, we're looking at, and this slide shows on the upper part the installed capacity for scenario 1 and 2 in 2045. And then on the lower side of the slide, how the electricity production actually will be divided between the different type of resources. So, and here you can notice the significant difference that's quite popular to discuss, where how much do you get out of 1 megawatt of hydro, nuclear, wind, or solar? And quite a big difference in terms of utilization, depending on various factors, of course. But the key element that I will come to later on in the study is also what Derlan saw, that with a completely new mix, with a lot less of hydro and nuclear, and in our case, we basically have no coal, but we've had something called CHP, combined heat and power, because a lot of the cities in Sweden are heated by district heating from CHP plants. So those have been very reliable as well as part of the electrical system mix. But going forward, that would be quite a small portion of the total rotating mass in the grid. And in both cases, you can see with the nuclear, still the most significant increase in power production will come from onshore wind, and also quite a significant portion of the electricity produced over the year. If we would go with this scenario without nuclear and basically close all the nuclear we have in Sweden, then we would also need a significant amount of offshore wind, and then that portion will be a very significant part of the production in the end. And as you can see in this case, which is quite one of these areas where people who are concerned about too much renewables see that almost none of this electricity will be produced by production facilities with rotating mass, which is one of the key elements to keep an electricity system stable. Whereas in this case, the nuclear will be here, and we have also almost about 50% of the energy being produced by those kind of resources. But looking at that is not enough. So the core of the study was actually to see with these two scenarios what is the amount of long duration energy storage that would be needed. And to really be able to take that question to the next level, we said that weather is very, very crucial in this, obviously from the solar and the wind perspective, but also in a country like Sweden, where weather also actually influences the consumption needs, both on a seasonal level, but also day and night. So we had a thesis work at Uppsala University to study and simulate 35 different typical weather years that we have statistics upon. And out of those, look at, as you can see on the left-hand side, over a full year, the assumed consumption and production on an hourly level. So basically, we have a bit more than 8,700 data points over the year here. And those look fairly stable and nice at a glance from a helicopter perspective. But if you actually start to look at the difference, you can see that, and this is clear, with this system, there will always be quite significant discrepancy between production and consumption. And that is the error that typically hydropower in Sweden has been solving. And that is possible if the hydropower resource is significant enough in terms of the discrepancy between the two here. So from an analysis point of view, we only looked at the deficits. When is the consumption need lower than the production plan from the systems? And we can see that those situations or occasions are more than hundreds of events on an annual basis. And they're quite long also in terms of hours. So even a couple of hundred hours of duration for a single event. And even more interesting is that because most people believe that with nuclear, we would solve the problem, but that's not the case. Basically, the deficit will be, the patterns will be very similar. And the simple explanation is that nuclear is a very plannable resource, but it's typically not used as a controllable resource like hydropower, which means that if there's discrepancy between production and consumption, to my knowledge, only France is using their nuclear power plants for controlling and compensating for that discrepancy. So nuclear, the way Sweden has been using it and most other parts of the world, is not a suitable solution for controllability. And then to put this, because this was a thesis work for two engineering graduates at master's level, we also emphasized the need for taking engineering approach on the result. And there were two aspects. We didn't want to have a result that didn't count on that there will be other technical solutions in the future. So flexibility, we said we don't want to estimate or assume that there will be or exactly what type of flexibility resource there will be in the future, so far away from today. But we can count on that there will be different types, everything from vehicle to grid to utilizing car batteries to flexible loads that are prepared to disconnect if they get paid for that, etc., etc. So in the study, we asked the students to take a look and assume that in every instant, where every event there was a deficit of how many minutes did you?
Oh, sorry.
5?
Yes, yes.
Okay, I'll rush then. Yeah, so we asked them to assume that flexibility will solve the first up to the first 8 hours, and then also we asked them to not look at the worst case, but actually exclude all the way down to 60 to 40% of the worst case scenarios. And then in the end, we said, okay, make some average assumption here. So with 4 hours of flexibility and then 80% of the cases assumed what would the capacity be needed and the amount of energy needed. And we ended up with something between 2,000 and 4,000 megawatts of energy storage capability. And the energy need would be between 20 and 40 gigawatt hour. So that was the rough summary, and regardless of which type of mix that we will have in Sweden in the future. And also in Europe, we don't have we've separated grid operation from production of electricity. So we have a slightly challenge in terms of market design and so on, since we've divided it, and it's a little bit more tricky for us to see who is really in charge of this. So we are lacking some of the market designs for managing this future dilemma. It's a society challenge, but who picks up the bill or who gets paid for solving the problem? I realized that I should, because I think what's even more important for you is actually our projects. So this is one of the projects that we're now, and this is not in operation yet. We are into the development phase, but this is a photo from above, and in the forefront you see a quarry, and in the end of the picture you see a nearby lake. And this project is in the south of Sweden, and fairly small ratings in the first two projects that we have in Sweden. So this is only 30 megawatt plus minus. That's really limited by the grid connection because we want to move as quickly as possible into the market. We have about 250,000 cubic meters at the upper level, and it will only vary the level of the lake of about let's see, 3 inches in that range. And we get about 70 megawatt hours in this project. And as you can see, we have the height difference of about 140 meters, only with a distance of about 600 meters. It's really an ideal location for a cost-efficient solution, and we're able to utilize very much existing infrastructure. Our other projects also utilizing a quarry. This one is just recently been completed the operations. It's fully dry, as you can see in the picture. In this project also, we have been funded by European Union with a 20 million euro grant for the construction works, development and construction works. And this is truly in a mining environment. And this is in the area of Norberg. And for those of you who are looking at historical sites, I think Norberg is probably getting on the list. And I don't know exactly how many centuries of mining operation there have been, but there are several centuries. One of the really oldest part of Europe where mining has been. But unfortunately, in the 80s, all the mining activities were closed. And this illustration done by our geologist is very simplified, but it shows, and it's a huge former mining system that over the years now, since the 80s, has been filled up with water. So groundwater is now almost at the level of the ground level. We have about 10 meters, 10, 15 meters approximately between ground level and the existing groundwater level. The query from the photo is this piece up here. And then we have a number of shafts, and we've investigated them and decided that this is the shaft that we will go for. And from this quarry, we will drive a ramp. So this ramp is not existing, but then we also will locate the machinery at about between 100 to 150 meters height difference. So very much of the mining system will be kept water filled. There's many millions of cubic meters of water down here. In our plans, we plan to pump about 2.5 million cubic meters of water out of the mine, so we get the right height difference. And then we plan to keep about 500,000 cubic meters of water to be used for the actual operation back and forth. So that is the system. And we're now into the environmental permitting phase in both projects. And the first project has already concluded what's called the consultation process. And we're just starting the consultation process in this project. And the concept has been considered as so innovative from EU perspective that the EU Innovation Fund is now supporting us with an investment grant of 20 million euro. My last slide is very quickly about what we've done together with Dareland and MTU so far in the US. And here you can see the different aspects that we are as Mine Storage doing in our way of working in the first phase, the qualification phase. And the first area where MTU was really instrumental, that was when we started to look at nearby closed mines. And I recall it was about 30,000 mines that we gathered data that we got from MTU. And then our geologists did a lot of data crunching on that to figure out which of the sites that would be most interesting. The second part was, and this is from one of the sites that we actually found 2 open pits where we could have a very attractive system without having to go below ground like we did in one of the Swedish project, which would be a very interesting pilot project for the US market. We also, together with the knowledge of MTU, did a number of different type of commercial or financial analysis of an energy storage in the region, because the rules and the regulations are completely different in the US compared to Europe, and also you have quite different conditions in different parts of the US. So this was definitely something that was a main contribution from the team from Dareland. And that is just a quick example of the way that we work. And as I said, we have Mine Storage way of working, where we start from the top level and looking at the 5 different areas in terms of mine and sites, the commercial aspect, the market analysis, of course, rights and regulation, which was one of the key elements when we started to investigate a fewer sites out of those 30,000. We talked about bring it down to a handful and start to contact landowners to be able to see that we will get land rights for this. So I think I've taken all my time. So by that, I'll thank you very much for your attention, and hope to hear some interesting, challenging questions.
Yes.